Okay, so a quick recall of what we saw until now in a summary would be to find the shortest path. We can use the algorithms that we learned until now, DFS and BFS. But the problem is if we use DFS, we'll definitely find a path, but that may not be the shortest. So we cannot terminate our algorithm as soon as we find this first path. And because of that, we need to do some post-processing to keep on finding the paths until we explored all the vertices of the graph that's given to us. And then with this post-processing, we'll compare the weights of all different paths and then choose the minimum one. A lot of work, and because of this additional work that we got to do, it's very inefficient. And so although we can use DFS for weighted, unweighted, directed, undirected, all those types of graphs, but it's just inefficient to use it to find shortest path using DFS. We saw that for BFS, breadth first search, it is good for unweighted graphs. And for unweighted graphs, as soon as we find the first path, that's the shortest path and we can exit. So it's definitely what we want to do, and while we are finding the shortest path. So BFS could be used if it's an unweighted graph. But the problem of using BFS with the weighted graph is that the weights might not be in the ascending order. So although you set the priority of exploring BFS as explore the edge with the shortest weight first, but then the recurrent priorities might not be aligned with your first level of priorities. And that's why BFS will not work for unweighted graphs. BFS will not work for weighted graphs. It will work for only unweighted graphs. So if your edges has weights, we have got the problem and the BFS will not work. So now moving forward, we need some more efficient and better algorithms that will allow us to find the shortest path, correct? And that's the reason we are going to see two most popular shortest path algorithms, Dijkstra's algorithm and Bell-Manford algorithm. Now, let's first start with exploring what is the Dijkstra's algorithm. So a Dijkstra's algorithm gives us a better approach for shortest path for unweighted graphs and single source shortest path graphs problems could be solved using this Dijkstra's algorithm. If you remember, we classified our shortest path problems into multiple categories: all pair, single source, single destination, single source, and single destinations. These four categories. So Dijkstra's algorithm is mostly used for the category of single source. So in this problem, we have a graph. We pick a source and we want to find the shortest path to all the other vertices in the graph. Now, I would say to begin with, Dijkstra's algorithm assumes That we do not have negative edges. We do not have negative cycles. There are some modified versions of Dijkstra's algorithm that can make it work for negative edges if you pre-process something. But definitely Dijkstra's algorithm doesn't work for negative cycles. Now, we already saw in our previous class that what would a negative cycle mean in a graph. There could be a graph where you don't have a negative cycle, but you just have a negative edge. And in that case, there could be some workaround that we can do. So it's important to understand negative cycle and negative edge is both different. There cannot be a negative cycle without a negative edge, but every graph with a negative edge does not necessarily mean that it's a graph with negative cycle. So if you want to find the shortest path from one node to all other nodes, then Dijkstra's algorithm is good. So what is the key idea behind the Dijkstra's algorithm? Dijkstra's algorithm is a greedy approach. And we will soon see why it is called a greedy approach. It's a shortcut we want to take to find the shortest path. And Dijkstra's algorithm allows us to do that in a very sophisticated and fast way. The complexity of Dijkstra's algorithm is very efficient. And that's why it's one of the reasons that Dijkstra's algorithm is very popular in real world. And you find people talking about it now and then when they are solving shortest path problems. They would prefer to use Dijkstra's algorithm at all the places where they can use Dijkstra's algorithm. So if your graph does not have negative edges, by negative edges, it's definitely negative weights of your edges. And if your graph does not have negative cycles, then you want to use Dijkstra's algorithm to find single source to the shortest path from a single source to all other vertices in the graph. So the key idea behind the Dijkstra's algorithm is that first, we keep track of the shortest path from the source to each vertex. So we keep exploring the graph from the source to all different vertex, and you keep track of the shortest path. By keeping track, it means as soon as you find anything that's more shorter than already you saw before, then you will update that to the new one. So that's this recurrent update on finding new information is what we mean by keeping track. That's what we want to do in the Dijkstra's algorithm. And the second, we want to use the above info that we collect by keeping track of the shortest path to compute shortest path to neighbors of these vertices. So as you see, graph is an interlinked structure, right? So from source, if you can reach to these two vertices, A and B, then you find out, okay, what is the fastest way to reach A and B? Now you seal that. Once you find the fastest way to reach this node, let's say, for example, B from A, you seal that. Then with that assumption that you already know the paths to reach from A to B in the fastest way possible. Now from B, you explore what are the other nodes that you can reach from B. Let's say E is one of the nodes that you can reach from B. Then the shortest path to reach from A to E is already assuming that the shortest path from reaching A to B is with whatever information you have in your pocket. And then, so your problem is reduced. The problem of finding the shortest path from A to E is now reduced to the problem of finding the shortest path from B to E. And so if you imagine a graph to be an hierarchy of decisions that you are making, and every time you find out the shortest path from one source to its adjacent neighbors, you log that, and then you proceed with that information with you when you are when you are exploring the other paths from these child adjacent vertices. That's the reason we call this approach as a greedy approach, right? Now you see why that word greedy is coming from. Dijkstra's is a greedy algorithm. The good part of Dijkstra's is its amazing low complexity. We are able to run Dijkstra's algorithm with a complexity of big O of V log V, where V is number of vertices, plus E. Now, we already discussed in our previous module, what is the relation between V and E if the graph is a complete graph. And we saw that E is always less than, we saw that E is always less than equal to V into V minus 1 by 2 if the graph is undirected. But if the graph is directed, as there can be two different possible edges that exist between two vertices, then we saw that it will be double of what if it's undirected. And that's why we can say it's proportional to V square if it's a directed graph. Now, with this relation in our mind between E and V, we can say that E is proportional to V square if it's fully connected graph. And that's how the complexity of running a Dijkstra's algorithm look like. Now, knowing that, okay, this is a good complexity, running something, finding a shortest path in the complexity of V square, right? Because this will be then equivalent to big O of V square if you take the bigger, the factor that accounts for the most. Then also depending upon what type of data structure are you using to store this graph, it might change. So it might be V log V, or even this could be V square. But overall, in worst case, it would be big O of V square, which is a very good complexity to find the shortest path. Now let's see what is an algorithm and how can we get to finding the shortest path with this complexity. So what we are going to do to learn this algorithm is first we'll take an example. We will walk through the process of finding the shortest path in that example. When we are doing that, I want you to note down the steps that we are logically performing. Once you have the steps that we are logically performing, that's your algorithm. From this algorithm, the next step is to write your pseudocode. Same as what we did in our previous module when we were coding for DFS and DFS. We are going to follow this process of first looking at example, learning from this example to write your algorithm. From algorithm, write your pseudocode, and definitely from pseudocode, it's then very easy to write the program in any language that you want, C++, Python, Java, anything, doesn't matter. So we are going to go through this. If you have any questions while we go through that, then mark down your questions, email them to me. It's very important that you understand each and every step of this process in order to learn the algorithm from its meaning. Learn the algorithm by understanding it and not by remembering just different steps of an algorithm. So you don't want to memorize the algorithm, but you want to understand the algorithm to learn. Okay, so then let's take our example. I am going to draw a graph, which we will be referring again throughout this example, in which we want to find the shortest path. It is preferable if you want to scratch pad this graph on your own notes as well, because then you can look at it and follow me while I'm talking about it. CH, A, we have E, we have G. This is a weighted directed graph. So we have weights to our edges, 20, 10. We have A connected to G with the weight of 90. We have G connected to A with the weight of 20. We have A connected to D with the weight of 80. We have a bidirectional edge between C and D with the weight of 40. Have C connected to H with the weight of 20. F to C with the weight of 10. I'm taking a complex enough graph in our example because I really want you to understand this process and to derive your own algorithm once you understand this process. F is connected to D with the weight of 40. What else we have here? E is connected to D with the weight of 50. E is connected to G with the weight of 30. And D is connected to G with the weight of 20. Okay, please do draw this graph in your own notes so that in that way this graph could be always in front of you while we are walking through this example. So what we are going to do is, first we are going to start. So our source is A and our task at hand is to find the shortest path to all other edges. So find the shortest path to B, C, D, E, F, G, H from A. What is the shortest path? That's what we want to find. So what we'll be doing is we will be using, while we walk through this example, we will be using two important things. So first is because our source is A, we want to start from A. We have this A, B. Let me not use that's a very big eraser. Okay. Let me not use the arrow mark because then it would confuse you with an edge. A, B, C, D, E, F, G, and H. These are, I'm just marking our graph so that it doesn't interfere. It's a better spacing. I don't want to cramp up at the edge. E, F, G, H. Okay. So these are our vertices. If to walk through this example, first we are going to take all these vertices. We are going to start from A. And for each of these vertices, we are going to note two main important information. First is the weights. What is the weight of reaching to this vertices from the A until our knowledge, with our knowledge until now. And the second is what is the parent of this vertices. So if we know the parent of all the vertices in the path, we know basically what this path consists of. So we are storing the weight, the minimum weight of a path and the path, both information itself. In order to do that, the way we will write it as first we'll write the numerator as the weight, the total weight to reach. So the weight to reach from A to A is 0. And we will write the parent because our A is our source. Let's say the parent of A is A itself because that's our root node, which we can say that. But then the parent of B, C, D, and E is the parent of these nodes along the shortest path. That's what we want to find. So we have these two information where the numerator is the weight, weight sum, and the denominator is the parent. Understood? Okay. So this to information, while we are writing an algorithm, we might need to store it in some type of data structure. That's the goal of proceeding with that. Now with this, now knowing that the numerator is the weight and the denominator is the parent, initially when we start, what is our state? Do we know what's the weight of reaching A to B? Nope, because before we start, we don't know anything. So let's initialize all the weights to reach all the nodes, or the weights of the shortest path to reach all the vertices as infinity. And parents, because we don't know what is the parent along the shortest path when we start. That's our goal. That's what we want to find out. We initialize the parents of all the nodes along the shortest path as -1. Now when we start, because A is our source, we are at A. What we do is we look at all the adjacent vertices from A. So what are the vertices that can be reached from A? And then we take a note of that. So in our first iteration, what we'll be doing is, the node that we are considering is A in our first iteration. And we are parsing, we are finding what are the adjacent vertices that can be reached from A. And because they are the adjacent vertices that can be reached from A, definitely it's common sense that A is parent of these all nodes. So we are saying that, okay, if we pay the cost of 20, with the cost of 20, we can reach B from A. Can we reach C from A? No. Can we directly? By reach, I mean directly. We can reach just B, D. So if we pay cost of 80, we can reach D from A. Sorry, A is the parent of all this, and denominator will be storing the parent. And if we pay cost of 90, then we can reach G from A. These are the three places we can reach from A. Remaining things will be same as what we initially set them. So that will be same as our initialization. Then once we have this information at this iteration, what we will do is we'll look at the weights that we have. We'll look at the information that we have at our hand in this iteration, and we'll pick the minimum. So here the minimum is 20, between 20, 80, and 90, the minimum is 20, right? So for our next iteration, we will move to, because that's B, we decide to move to B. So now we are at B, and we look at what are the things that you can reach from B and how much will that cost. So from B, first the cost to reach B is already 20 as of now. That's what we know. And we are reaching to B from A. Now, given that we already incurred this 20 as our cost, from B further, where all we can go. So we see, as we see in the graph, from B, you can further go to just one node. That's F, adjacent, right? So remaining everything would be same, but for F, now the additional cost that's incurring is 10, but already to reach to B, you incurred cost of 20. So the total cost to reach F will be 20 plus 10. That's 30. So that's what we'll note down. The total, the sum of the weights of the edges, that's 30. And now the parent of F is nothing but B. So at the completion of this iteration, you will have 20 by A. This will be same. I'm just saying it infinity, but definitely there is no parent yet. So infinity definitely also means that there is no parent. Then we have this as same because it's untouched. This is infinity, this is untouched, it's the same, and this is infinity again at the end. Now that we are at B, which is the minimum from the information that we have at the hand? Minimum and unvisited. B is already now visited. F, right? F is the minimum and unvisited node. So next what we do is we pick F. We decide to move to F, our current pointer. Now that we are at F, now let's look at what are the adjacent nodes that can be reached from F. From F, as you see in that figure, you can reach to C, you can reach to D. Is there anything else that you can reach from F? Nothing else. So if you want to reach to C, how much will it cost? First, we know that the cost to reach F is 30. So anything, the edge weight of the node that we want to reach out from F will be in addition to this 30. So if you want to reach from F, if you want to reach C, then it's additional 10. So it's 30 plus 10, which is 40. And then F will be the parent for C. The other node that you can reach from F is D, where let's see. So here comes an important step. Now, if we want to reach D from F, then it's going to cost us 30 to reach to F, and then additional 40 because that's the edge weight between the F and D. So 40 plus 30, 70. So if we want to reach this node D by parent as F, it's going to cost us 70, which is less than what originally we had here, right? What we have is this. What we have is it will cost us 80, but now we have found out a better path to reach to D with a lesser cost. And that's why we'll update that as, okay, I have found out a better path, which will cost us only 70, not 80. And the parent along this path will be F. The parent of this node to reach D will be F. Remaining information will just keep the same because there is no other node that we can reach from F. And now we have explored B, F, which is the next minimum node is the C because C has 40. So if you have to compare 40, 70, and 90, C is the node which we want to go next to. Let's pick C. Time to go to next whiteboard. So let me use the red marker. Okay, so now we traverse to C, then the next iteration. This is where I said having a local copy of that graph would help. I don't want to keep drawing graph again and again. So I'm assuming you have a local copy that you're looking at. So next iteration, we went to C. Now from C, where all we can go? Let's see. From C, we can go either back to F, but F is already explored. From C, you can go to D. From C, you can go to H. Those are your three options. Now, you know that the cost to reach D is 70 if F is its parent. Is there a way? The cost to reach C is 40. So if you want to reach D via C, then it's originally the cost to reach C is 40 plus the edge weight from C to D is 40. So 40 plus 40, that's 80, which is not smaller than 70. So we don't want to update that. We have this new path to reach D, but that new path is not shorter than what we already know. That's why we are not going to update the path to reach D. But H is, on the other hand, totally unexplored. The cost to reach H is infinity. And definitely reaching to F in anything which is less than infinity is going to benefit us. And that's why we update the cost to reach H with the cost to reach C, that is 40, plus the edge weight from C to H, which is 20. 40 plus 20, 60. So let's say we have this B, C, D, E, F, G, H. And now we are at this node A is the source. Now we are at this node C, which we are exploring in this iteration. And we want to update H with the cost of 60, 40 plus 20. And the parent is C. The remaining on information here is the same. I'm just copying it from the previous iteration. F 50. Cost to reach. Do we have everything from the previous iteration? Twenty by A, 40 by F. Oh, no, sorry. This would rather be 70 by, okay. I want to, we need to verify if the cost to reach D from C is anything better than 70. The cost to reach C is 40, and the cost to reach C from D is additional, D from C is additional 40. That will lead us to 80. So nope. This will just remain this. We don't want to update it, but rather it would remain 70, same as 70 from reaching it from F. We just updated the H. Infinity 30 by A, 90 by A, 60 by C. Okay, perfect. And then what are the nodes that we already visited? Let's take a note of that. We visited B, C, and F. And now with this iteration, we are done with C. Now it's time to pick the next minimum, which is now D because 70, no, which is now H because 60 is less than 70 and 90. So we will be picking H. I am doing this online because I think the example I have is the different. So let's do it together. I think the graph that we have is the different from the example I have. So, okay, so now if H is our next node, so we move our pointer to H. From H, where can we reach out to? Is there any unexplored node that we can reach from H? Nope. Everything we can from H, that's the dead end. You can't reach anything from H. So basically everything will remain same. And now we have already explored H. It's time to next explore the node which is smaller, 70 and 90. So 70 is smaller. Next, we will take D into our consideration. Now from D, where all can you reach from D? From D, you can reach to G. The cost to reach D is, as of now, what we know is 70. So anything that we reach out from D will be an addition to this 70. The cost to reach D is 70. So from D, if you want to reach G, it's 70 plus the edge weight of D to G, that's 20. So 70, 80, 90, that would be 90. Now G, if you see, it can be reached from A with the weight of 90. So we are not doing anything good. Is there any other thing that you can reach out from D? You can go to C, but C is already explored. We have explored A, B, F, C, H, and D. So we assume that we already know the shortest path until this, until H. So we know the shortest path to B, F, C, and H already. So we don't want to touch the C again. And the cost to reach G from D is 70, 80, 90, as we just calculated, and 90 is not less than 90, right? So we won't be updating that. We'll just leave it the same. So after we explore D, we are at this. Infinity, we have not yet found a node to find our way to E. And we have already seen these all. So now we are just left with G, which we will be seeing next. Picking G as our next point. If we move to G, where all you can reach from G? Can you reach to any new node that we have not yet explored? You can reach to A. A is already done, and that's it. You cannot reach anywhere else apart from that. So basically, we will not change. This iteration will not impact anything because there is no new node. The only unexplored node is E at this point, and E cannot be reached from G. So everything will just remain the same. Okay, so now that's it. Then you have explored all the node. Nothing is remaining. E is infinity, which the algorithm would end because E cannot be reached. There is no shortest path to reach E from A. And if you see in the graph, you would see that A and E cannot be connected in any way. You cannot reach E from A in any possible way in this graph. That's something like we talked about reaching Miami to Bahamas by road. So that's the reason at the completion of this algorithm, E still stands with that E does not have any parents because there is no shortest path that could be found to E. That's why we still have infinity. But we found the shortest path to all other nodes. So if you want to reach B from A, the shortest path is directly reach with A as the parent, reach B, and it will cost us 20. If we want to reach C, Then the path is C's parent is F. So we would, in order to reach C, we will have the parent of the parent of C is F. But then what we need to see is, okay, so what is the parent of F, right? The parent of F is nothing but B. We can see from here. The parent of B is nothing but A. So this is the shortest path to reach C from A, B, F, and C. And if we look here, A to B will cost us 20, B to F will cost us another 10, so that's 30. And F to C will cost us another 10, so that's 40. So the shortest path to reach C from A is costing us 40, and we know the path of it. In the same way, the shortest path to reach D. Now, I don't want to bore you to verify the same thing again, but I think you guys are getting the concept or getting the edge at what we are trying to do here. So we are just verifying the things. And this is how you would know the shortest path, as well as you will know the weight of the shortest path that you're taking. That's it. So this is basically the algorithm. Now, doing this process, it's tedious by hand, but the benefit of that is when you do this process, then you are trying to frame the logical steps from it. So now I hope that all of you have noted down the logical steps while we are processing each of these iterations. And now let's write our logical steps that we did while going through the Dijkstras. So let's write our algorithm. First step, so for each vertex, we want to keep two labels, right? As we saw here, we are keeping those two labels, numerator and denominator. That's the data structures we want to maintain. So first we should know what we want to maintain. So for each vertex, keep two labels. Different, you can store them in different ways, arrays, vector, whatever you like. But this is an information we want to store. We want to store weight for each vertex, and we want to store by weight, it's the total weight, and we want to store the parent or the source or the adjacent node from where we reached out to this node. So this two information is what we want to store. Now, step one, what is the first step that we did while we are writing this example? The first most step is to initialize, right? So that's exactly what we need to do while we are writing our algorithm. So step one, initialization. What did we do in initialization? First, we marked every vertex as unvisited. So every vertex is marked as unvisited. By marking them as unvisited, we marked it as the weights to reach until there is infinity and the parent is -1. That's how we'll be updating this label, and that's how we'll be letting computer know that these vertex are yet unvisited. Other thing that we did that we want to do in initialization is that the shortest path from the source to all is set equals to infinity. That's what we did here while we were drawing it. The first step, all the vertices marked as unvisited, because then slowly as we proceed along our iterations, right, one to the other, then we'll be visiting different vertices. So that the visiting order is nothing but the order in which our pointer was moving when we are going through this example, right? I was moving this pointer to different node. That's our visiting order. But initially, when we start, we have not visited anything. So it's a blank slate, and that's what we initialize. What is one more thing that we need to initialize? The last thing. The source of all the vertices is -1, right? So we are setting parent or source is equal to -1. You can choose the digit of your interest. Definitely, yes, this is the one, but there's something, do we need to initialize anything else? Think, is there anything else we need to initialize? You are writing algorithm to do the steps that we did while we were walking through this example. What are the things we need when you are writing algorithm for that is what we are anticipating and initializing. So we needed this data structure to store this two information, which is the parent and the total weight. We needed a data structure to store the visited order because here you wrote it row by row, but you need to say computer something that what things are visited and what is the next step that you want to do. There's something else you would need in order to do this. What did we do? What did we do in each iteration? We looked at it and we picked the node that has the minimum weight as our next node to visit, right? We moved our pointer in the graph from the node to its adjacent node, which had the minimum weight to reach it. So we looked at this iteration and we picked, okay, we compared all the unvisited, like 70, 30, 90, 60, 20, 40. Out of that, some of them were visited, which had the blue underline. But the one, those are not visited. We looked at those and we picked the minimum one to take it as a vector of our next iteration. If you want to do this step in computer, what is the thing that you would need to do? So you will be using a data structure, right, to store the nodes. And now you want to somehow amend this data structure that at every iteration, you can go ahead and pick its minimum. So this data structure that you want to use can be as simple as array, right? In that case, you need to initialize this array. And what you can do is take all the elements of the array and find out the minimum of that array. So what is the complexity of finding a minimum element in an array? You need to parse through all the elements of array at least once. So if the array is of size n, then the complexity is big O of n. You can, you have to do this at an every iteration. So is there any smart data structure that you can use to find the minimum element at a better complexity than big O of n? Yes, if you're thinking a data structure that we can use as priority queue, then it's correct. But underneath the priority queue, you can use min heap to program a priority queue. So we can use min heap to program priority queue, and that will give us a complexity of, we already learned this in our heaps module, big O of log n. To find the, if you have a heap, then to rearrange to solve the one violation in that heap is big O of log n. And finding the minimum element from the heap is just big O of 1, because then you just remove the topmost element. In the min heap, the topmost element is the minimum element. So using priority queue is a better option rather than using array. And that's why if we want to use priority queue, then we need to initialize the priority queue in our initialization step. So how we are going to initialize the priority queue is push all nodes into a priority queue based on distance. So this the priority of this priority queue is nothing but the distance or the cost or the sum of the weights. So the elements inside this priority queue are arranged in a way that the minimum cost incurring element is at the head, and then so on. But initially we push all the elements, and what are initial weights is infinity, so all the elements will be there in that priority queue with that infinity, and a will be at the head because the 0 is less than infinity, and the cost to reach a from a is 0. So the distance or cost, whatever the term that you want to use for the edges, that's 0, and that's where the initial state of our priority queue will be nothing but all these elements inside the queue with a at the head, and then we have all the remaining elements in the queue with their distance as infinity or the cost as infinity. But as we explore, or as we give weights to this elements inside, what we did in this each of these iterations, the elements inside this priority queue will be using min heap, and they'll be rearranging themselves, that the head of this priority queue is always the smallest element, and that will allow us to pick our element for the next iteration. As we did manually, we picked the smallest, the element, the vertices that had the smallest edge, and that was unvisited in our next. And initially, because all the elements are unvisited, they are in the queue, but later when we are done with one of the element, we'll start popping the elements out from our queue. So if you are done with a over here in this first iteration, right, we are done with a, so then we'll pop off a, and then our head will be the next smallest element. So I am thinking that all of you are getting this idea of what we are planning to do, and you are with me on the thought process of these are the things that we need to initialize. So now we are done with the step of initialization. What's our next important step? Well, we have inserted everything into our queue. We got to find out when to pop things out of the queue, or when to exit things, remove things from the queue, right? So our next step is always pop the vertex with the smallest cost or distance among the queued vertices. We'll be also marking it as visited, but this is, so basically this step is the step in our example which represented marking this pointer, right? We need to figure out which is the vertex that we are going to process next, and that's exactly what we want to pop out outside the queue. Step 3. Now we are just left with a single most important step, that is to update all adjacent vertices of current visiting node. So this current visiting node is what we pop from the step 2 with the shortest path from source. This is what exactly we did in each of our iteration. We looked at what are the nodes that are adjacent and could be reached from the node that we are handling in this iteration, for example, D over here. Then we looked at what are the things which we can reach from D, and we looked at, okay, is there any shorter path to reach at those nodes from D, from compared to the knowledge that we already know. If we find a shorter path, we updated that. So that's a recurrent step which we'll be doing, step 3, until we are done exploring all the possible, nodes in the graph. In this case, that would be the case when there is no element remaining in the queue, because we are popping every time we are done with one of the elements. So as you see here in the example, we visited A, B, F, C, H, D, G, and E is infinity, it cannot be reached. So once we are done with all this, our queue would be empty. So these are our steps, where step 3 is the recurrent case, and our base case of this or our clue to exit is nothing but until queue, you can call it as priority queue, becomes empty. That's our clue of we are done with everything. So this is the 3 most important steps in our algorithm. Now that we know the algorithm, let's write down the pseudocode. Finally, right? What do you want to name our pseudocode? Int shortest path. What are the arguments we would need for our pseudocode? What are the things that we need to take as an input? The graph itself, the most important. Graph G. We need the source vertex. Yes. Let's call it S. And if we are writing, if the goal of our algorithm is single source to single destination, then we need the end vertex. What's the destination? But if the goal of our algorithm is single source to finding the shortest path to all other vertices, then we don't need. We'll see there is a minor modification to the algorithm in each of those cases when you want to find all other vertices versus when you want to find just shortest path to a single destination. Definitely, as you imagine, the shortest path to single destination algorithm will terminate as soon as you find the shortest path from source to that destination. So there might be an additional termination condition, while the termination condition of shortest path from single source to all other vertices would be more broad, because until you are done processing all the vertices, you won't be done. So we'll see both the modifications. First, let's assume that we are not concerned with any single destination and we want to find the shortest path to all other vertices. So then, as we saw in our step 1 of algorithm, the initialization, we would proceed with doing our initialization steps in our pseudocode. So mark all vertices unvisited, which can also be said like you can have this visited as an array, and then you can have number of edges, the visited as an array of the size of number of vertices, and then you can initialize that array to 0. So something like this is what I mean by that. From among the 3 things that we did in our initialization step, then set the shortest path to all vertices as infinity. What else we did? We set parent. So the shortest path can be again another array, same as visited, and then you set infinity. You can't set as infinity in computers, but then you can initialize that to a really big number, or the big number that your data type, the biggest number that your data type could accommodate. And that would be same as in representing infinity. We set the parent of all the vertices. So if this is an array, then SP is an array, parent is an array, the parent of all vertices as -1. And finally, in step 3, what we did was push all vertices into priority queue. Let's say that the priority queue is something we initialize outside this function of shortest path. It could be the global initialization of our program and we are using it. If it's not a global initialization of priority queue, you might also want to initialize the priority queue before pushing all the elements into that. Before using that priority queue, you might want to define and then initialize. So I'm assuming that it's already defined somewhere else and we are directly initializing it. Then after this, the step 2 and step 3 are something that's happening recurrently again and again for all the iterations, as we already saw while we were manually walking through the algorithm. So this, because it's happening recurrently, let's use while loop. While priority queue is not empty. So as soon as it's empty, it will exit this loop, but until it's not empty, it will keep on doing the steps that we mentioned in this loop. And because we are finding shortest path to all other vertices in our graph, so this is the only condition that we would have. What we do is now inside this while loop, we will have for all unvisited neighbors W of V. So in a single iteration, which is the while loop, what we did was we went through and picked the unvisited neighbors of V. So if V was this node, V is our this node that we are picking. Then in this iteration, we went through and we picked the W. So W is the one which we process in that iteration, and that's what this for loop represents. So we went and saw, okay, what is unvisited, the one that didn't have the blue underline. And if it's unvisited, what we saw was if shortest path to W is greater than the shortest path to V plus weight of reaching W from V. So whatever we had originally there in the before iteration, if that was greater than the new weight that we calculate by reaching this node from V now. So if reaching W from V is cheaper than whatever W was reached from before in our, according to our previous knowledge, then we want to update that. So we updated that. So the shortest path of W is then shortest path to V, which is the weight to reach V plus this weight over here. So the weight of the edge itself. So weight to reach the parent, which we already know, plus the weight of this additional edge. And then we also set parent of W, we update the denominator, parent of W as V. And that's it. So we'll keep doing this same thing again and again until we empty our priority queue. Now, when you are doing this, every time you, what is wrong with this algorithm? Will this algorithm ever terminate? No, because we are not popping anything, right? We've set the termination condition to PQ is not empty. We fill the PQ, but we are not emptying PQ anywhere. So we need a step to reach to make progress towards our termination condition. That would be popping out elements. So every time we enter into, every time we have this, we enter into this while loop, we need somewhere we need to pop element from PQ. So as soon as we enter, we can say that pop vertex V, which is our vertex at hand. And V is also the head of that priority queue. So pop vertex V of PQ. And whenever you pop anything out of PQ, you also mark, because we are maintaining the visited array, we mark visited for this head, which is V, is equal to 1 now, because now V is already visited. Is this algorithm complete now? Is this pseudocode complete now? At the end of this, what would it return? It will have this, we are framing this nice arrays of FP, and we are framing this nice array of parent. So what we want to return at the end of this algorithm is, you can just return 0, and then you can print this arrays over here as your step, and then you can have this another print function where you can send this arrays and that function can print, and you can just return 0 to exit if the return type is int, or the return type could be void. You don't have to return anything. So there are many different ways on how you want to print the output. So basically what you want is whatever is the result in this. Those two are the things that we are updating along the algorithm. So the result of this, as we saw here in our example, at the end, whatever you have in this last row is what is the result of the whole algorithm, and this is what gives you the shortest path to all the nodes, right, as we computed here. So if you have SP and if you have your parent, then you can find the shortest path. So that's what you will print, you will return in the way you want to handle. So that's it. We are done with the shortest path finding algorithm using Dijkstra's if you want to find single source to all the destination. Now, what are the changes that we need to make in the pseudocode if you want to find single source to just a particular destination? So first is, we will definitely need our destination, right? Vertex D. We need to know what are we aiming to reach to. This all initialization will remain same. Yes, definitely. While loop, what there'll be some modifications, I think, as many of you are already thinking. There'll be definitely an additional condition to exit this while loop. We don't have to keep on running until the whole PQ is empty. As soon as you reach your destination, so we can say either if PQ is empty and path found, and path is not found. So only if the path is not found, only if your destination is not reached from source, until then it will keep running this loop. So if your PQ is non-empty and path is not found, until then it will keep enter this while loop. Now inside this while loop, will there be any changes? How will you identify that your destination is found? That's where you want to return, right? So there will be definitely, if you're thinking that you need some if condition in order to find out that your destination is found, that's correct. We need to add an if condition, and a better place to add this if condition. Let me use the black marker. Will be somewhere here. We need an additional if condition at this place before we jump into that for loop, where for loop will be an else of this if. I'm just going to squeeze this if condition over here because it's simplistic. So if your V, the vertex at hand, is equal to your D, that's your end vertex that you want to, that's your goal, to find the shortest path to. Then what you do is shortest path is found basically, and then you return the shortest path vector, you return the parent vector, and you exit from the algorithm. So if it's int that you want to return, then you would be returning only, so you would be printing the shortest path, and then you would be returning here or exiting the algorithm here. So either when you find the destination, or you keep proceeding further. So if you don't find the destination, then you move to the next iteration. In order to move to the next iteration, What you do is you see if for all the unvisited neighbors W of V, you go and pick the shortest, you go and calculate the shortest path that can be reached from V for all the nodes that you can reach from V. You see if there is any better path to reach this W, each of this W. There can be multiple nodes that you can reach from your V. So that's why we have a for loop. You go through all these nodes that you can reach from V and you see if there is any better path from already what you know. If yes, then you update that. If not, then you just proceed further. And then you go to the next V by picking the smallest one in the priority, by picking the smallest element at that iteration. That's automatically done by your priority queue. So as soon as you pop any element from the priority queue, the next head will automatically be the smallest one. So you're moving, when you are moving from one iteration to the other iteration, you have the smallest element as your V automatically because it's priority queue. And for each of this V, then you are having this for loop to update the shortest path. Okay, so now we are done with the pseudocode. What would be the complexity of the pseudocode? Is there any brave soul that is already onto finding the complexity? I think you'd already know the answer of what the complexity of Dijkstra is, as I already mentioned in the beginning. But the key challenge is how do you get that as a complexity? Okay, so with this algorithm, with this pseudocode over here, now you see that you have two loops, a while loop and a for loop. The while loop is going through all the elements in the priority queue. So the while loop is going through all the vertices. So definitely this while loop is incurring some cost related to number of vertices, that's V. Now, because this while loop is over priority queue, the cost of like maintaining the priority queue, having that minimum element at the head of the priority queue, we are managing our priority queue using min heap, and the max heapify operation of min heap is nothing but log of that data size, and here the data size we are operating over the vertices, so it's v log v is something that's been incurred by this while loop. Now what we are doing in this while loop is we are having a for loop, but it's very important to know that this for loop is not going, although it's within the while loop, what the additional cost that's been incurred by this for loop is not for each vertex. So to further explain that, now when we were walking through our manual steps of with this example, note that each edge is just touched once. We are not touching the edge, each edge for each vertex once, but rather we are touching each edge just once for all the vertices, right? Because once we mark it blue, then we don't touch it again. So although this for loop is within this while loop, but because we are not touching all the edges for each vertex, but rather we are touching only the edges that can be reached adjacent, or that is the neighbor of this vertex. And then once we move on to other vertex, then we are bothered with the neighbor of that vertex. We are no longer bothered about the other edges of all other vertices. Because of that, it's not multiplied by E. Rather, it is added. So at max, for whole graph, you will have E edges. And each edge, irrespective of when, you would at max touch each edge once, because each edge could lead to the neighbor of any vertex that is V once in this process. So that way we are adding it with number of edges. And that's it. It's big O of V log V plus E. That's the complexity of Dijkstra's algorithm, which is of the order of big O of V square, depending on if you're using how you are storing the graph, how dense the graph is, if the graph is complete graph or not. So depending on all these factors, it could be at max big O of V square, but accurately it's big O of V log V plus E. Okay, so if you have any questions on any of the topics that we discussed regarding the Dijkstra's algorithm, if you have any questions in the example, if you have any questions in the construction of the steps of algorithm itself, or if you have any questions in the pseudocode and its complexity analysis, then please email those questions to me. But before we move to the Bellman-Ford algorithm, I want to, did any one of you think that why did we initially said that Dijkstra's algorithm does not work for negative edges? And in order to make Dijkstra's algorithm work for negative edges, we have to do some modifications to it. But by its original form, it does not work for negative edges. Did any one of you think what would be the problem if we have negative edges and if we are using this Dijkstra's algorithm to find the shortest path in a graph with negative edges? I really hope so. Okay, so let's look at what's the problem. So first is, we all know that Dijkstra's algorithm is greedy, right? And I believe by now all of you understand what do we mean by greedy after looking at the algorithm itself. So Dijkstra's algorithm is greedy because we assume, or the algorithm assumes that once the vertex is marked as visited, the algorithm has found the shortest path to that vertex. So to descriptively say this, in our algorithm, in our pseudocode, we are maintaining this priority queue. And whenever we pop anything out of this priority queue, we are marking it as visited. And then we forget about it, right? Once we mark anything as visited, that's it. We don't touch it ever again. It's like this iterations over here. When we manually ran this algorithm, we just touched D only once. We just touched H only once. We just touched. So after this iteration, there'll be an iteration for E, which will, because E is not reachable from anything else, it will be there on our priority queue according to our pseudocode. That will be the last most element. But then infinity plus anything will be greater than infinity. So it will remain the last. When we visit this V as our node E, everything else will remain same, because anything that this E could bring to its adjacent vertices is infinity plus something. So that's the whole, that's where we see that all these vertices, A, B, C, D, E, F, G, H, everything, we just visited only once while we were iterating through it. And once we mark it as visited, then we forget about it. That's the whole reason that we call it as greedy algorithm. And once we visit it, we assume that we already found the shortest path to reach until that vertex. And then we are just bothered about anything above that. We don't go back and look at what happens before that. And because of this, like because of this assumption, we are able to reduce our cost to a big extent, because Dijkstra's is a greedy algorithm. we are able to run it at the cost of big O of V square, in the order of that. But then it has its own negation, so it has its own impact, right? So we cannot deal with the graph that has negative weights of its edges. Let's take an example of a graph, of a very simple graph with just 3 vertices. And let's say that the edges that connects these vertices have these weights. We want to take an example of negative edge because that's what we are looking at. So let's say that this is the graph for which we are using Dijkstra's, and our source is S. So we'll have, as we did before, we'll push all the vertices into our priority queue. The distance to reach source from source is 0, and the parent is A itself. Everything else will be initialized to 0, to infinity, and the parent as not yet found. In our first iteration, then we assume that yes, we are at A because 0 is less than both the infinities. From A, you can reach to B at the cost of phi, and A is the parent. From A, you can reach to C at the cost of 2. A is the parent. This remains the same. Now, then you take the minimum of this, right? So that's this over here, that's minimum. So in the next iteration, you take C. Now from C, is there any other neighbor or adjacent vertices that can be reached at the cheaper cost than the original one? No. So in this iteration, the inside for loop of this vertex C as V will go through the W's, but it won't find any W that's unvisited because there is no adjacent neighbor. So this loop for all unvisited neighbors W of V, with V as C, it doesn't have any W. Our third iteration, I'm just continuing over here. So in our third iteration, then we are done with this, we are done with this. In the first iteration, we are done with this. In our second iteration, the only thing that we are remaining is with this. So we'll take B. Now from B, when we are at B, we'll see what are this for loop, the inside one, will for all unvisited neighbors W of V. So for this B, the A is already visited, C is already visited, so B has a neighbor C, but that neighbor is not unvisited. And that's the whole reason when you apply this algorithm as it is to this graph that has negative edge, what the result you will get is, after this final iteration, will be right this. Because we are considering only all unvisited neighbors W of V. So this iteration will miss to account for this negative edge over here. So actually the cost of reaching the shortest path to reach C is not this, right? It's not this, but rather the shortest path to reach C is this, and that would cost us -5, while this will cost us 2. So in reality, this should be -5 by B, but we are not able, the algorithm is not able to give that as an output. And that's the reason, like this is the problem, why Dijkstra's algorithm does not work with negative edges. Now, I think Dijkstra's, everybody in this meeting needs to be super, super clear with solid concepts of understanding Dijkstra's, and you should be like, even if you are woke up at night, midnight in your sleep, you're okay, write an algorithm to code Dijkstra's. You should be able to write a code for that in any language, any one of your favorite language. To end it, I would like to give you another example, and then I want you to work through this example yourself. So in this, take this example and work through that example as what we worked through over this example right here, right? So take that example, do all the steps of manually processing all the iterations, then do the thinking process of what we did when we came out with those steps following the order of operations that we did while we were working through that example. You already know the pseudocode. So connect the steps that you're doing in that example while you are working on it on your own with the pseudocode over here. And that will actually help you to understand the process very deeply. So unless you get your hands dirty, you don't get all the treasure. So let's get your hands dirty. And this example is for you to work on yourself. So let's say that we have this graph with 6 vertices. The edges are directed and the weights of this edges is corresponding. A to E is 4, F to E is 6, D to F is 20, C to D is 14, E to D is 12. You have 2 more edges, E to D and D to E. E to D weight is 4 and D to E weight is 10. And there is one more edge from A to C with its weight as 11. When finally there is an edge from B to D with its edge weight as 2. Don't get confused with this edge weight. The 6 is edge weight for this, 2 is edge weight for this, 8 is edge weight for this, and 11 is edge weight for this. So now given this graph, if you have this graph as your input, then your task is to find the shortest path from A to F. No, let's make it a bit more interesting. let's work on finding the shortest path from F to A rather than A to F. And do all the steps manually that we did. I would be curious to find your answer that you get. While doing this, you might have some questions. So this is the whole process of making you think of the questions that even you don't know, right? I cannot answer your questions if you don't ask me questions, but you cannot ask questions until you know your questions. In order to know your questions, you need to work yourself, and that's how you go into this doubts, and then you have confusion, and then you have question. So only when you're doing it yourself, there are high chances of having that. So do it yourself. Just to make your life easier after you are done, let me give you the answer. The shortest path that you find from F to A is F, E, D, A. This should be your output of the shortest path. And the weight is this shortest path. The answer of your weight is 28. Now, with a small modification, if you change your algorithm, or if you continue doing the process for the further iterations to find the shortest path to all other nodes and not just A, with source as F, then you will end up with your last iteration that has this as answer. So F was your source, all other nodes A, B, C, D, E, F. This could be reached at the cost of, so as we already know, A will be reached at the cost of 28, and the parent vector of A is B. B should be reached at the cost of 32, parent vector will be C. C should be reached at the cost of 38, parent vector being B. D at the cost of 16, parent vertices being E. E should be reached at the cost of 6 from F, and F definitely to reach F from F is 0, and F is parent of itself because F is our source over here. So this should be your final answer if you process this graph over here until to find the shortest path for all the other vertices E, A, D, C, and D with your source as F. Hope you have fun doing this exercise and you learn while doing it. Bye-bye.